Okay, so we're now going to be focusing on AC analysis here, and we start this off with our discussion on sinusoids. Because basically when we're talking about AC analysis, this is typically our input. It's a sinusoid. Now, this really, I think, gets people a little confused at first, because you think sinusoid, you must think, oh, I'm going to mean a sine wave. But sinusoids are either cosine or sine. Now, let's just go back and remember some basic things about sinusoids here. So let's just start with a very simple cosine of 2t. And recall some things here for this. Well, actually, let's go ahead and put a 5 here. From trig, we should remember that the 5 we usually refer to as something called the amplitude, which we still do here. And you may not have referred to this in trig, but hopefully you did. This is actually what's referred to, that number in front is actually the angular frequency. And the units of this is radians per second. And we can remember here from this that we can get something that's called capital T, which is the period of our sine or cosine wave, and we get it by doing 2 pi divided by this number that's in front. So often I'll put it here as omega because it's the angular frequency. Omega is angular frequency. And so in this particular case, we would have that the period would be 2 pi over 2, which would be pi, and of course period is in the units of seconds. We also want to remember here frequency. Frequency is 1 over the period, and in this case we could get that this would be 1 over pi as my frequency, and the unit for frequency is in hertz. Now, there is something that people always mix up here, is that F and omega, they're both frequencies. It's just this is what's referred to as the angular frequency. And we just call F the frequency. And it's the units that are important here. The units for frequency are in hertz, and the units for omega are in radians per second. So what we'll often see here for a generic cosine function, for instance, we might have, I'll just have here f at t is equal to some amplitude a cosine omega t. And then this is my angular frequency. But another way you can write this, there's a relationship between the angular frequency and the frequency. Omega is equal to 2 pi times the frequency. So what we can do, and this is sometimes how it's written, is that sometimes we can just substitute this in here and we will write this as a cosine of 2 pi f times t. So you want to be familiar with both of these, and the key thing here, you want to be you want to make sure you understand the difference between angular frequency and frequency, and that there is an equation relating them. That's going to be very important in our computations and our problems that we're going to be examining in this module, because sometimes your problem will be giving you a frequency in hertz, and sometimes the problem will give you a frequency in radians per second, and you need to make sure that you have it in the right units when doing your computations. Okay, now the most generic way we can write a sinusoid would be some amplitude A cosine omega t plus theta. And here we've added one additional term here. This theta is referred to as a phase shift, because normally a cosine function looks like the following. You start up high, then you go down, then you come back up, then you go up high, then you come back down, and so on, in both directions, and it goes on forever. So this is a cosine function with no phase shift. Now I'll do a very simple case here. Actually, I'm not going to bother with a simple case here. What I'll do is I'll just draw another cosine wave here. So on and so on. Now this is still a cosine function. In fact, these two things have the same period / frequency. But this one has a phase shift. It's a phase shift to the left because normally what are we supposed to do? It's supposed to, cosine function starts at its highest value and then goes down. Well, the highest value occurs before x equals 0, occurs before in some negative time here. And so we have phase shifted this to the left here. And so we're actually going to have a special term we call that here. And so that is actually showing that it's the same graph, but it's actually been phase shifted. Now what's important to that is we can actually then say that actually cosine and sine have the same graph. One is just phase shifted. In fact, and this is I'm going to star this equation. This is going to be incredibly, putting 4 stars here. This is a very important identity. You want to put it in your, maybe your formulas, your list of equations. That the cosine, sorry, not cosine, I want to do this, that the sine function, sine of omega t, is equal to the cosine of omega t minus 90 degrees. So they're the same graph, it's just the sine function, the graph is the same as the cosine function, it's just we have to do a phase shift on the cosine function. And minus 90 degrees would be a phase shift of 90 degrees to the right. And what that would actually end up getting you, as I'll draw it as dotted here, if you moved 90 degrees to the right, you'd get the following. Which we know is what the sine function looks like, but that's also shifting this red curve 90 degrees to the right. And you might say shifting it 90 degrees to your right, you might say that doesn't make sense because you're thinking about rotation, but you can also think of it, if you want to convert the 90 degrees to radians, 90 degrees is pi over 2, so you're shifting it pi over 2 to the right, if that somehow makes more sense to you. All right, now we're not going to necessarily do a ton of graphing in this course, but it's definitely important to understand what these graphs look like and the fact that we have these angular frequencies, these periods, and these phase shifts, because these are all going to become very important to us. Now, depending on the textbook that's being used here, there's probably a section that's talking a lot about complex forcing functions and imaginary things, and it can get kind of nitty-gritty and a little detailed. So I wouldn't worry too much about that. Where we're going to really kind of dive in here is we're going to actually kind of begin a discussion on phasors. So anything before phasors you can somewhat kind of just skim, and if you don't understand it 100%, I wouldn't worry too much about it. Okay? Now, before we even talk about phasors, let's discuss what our goal is. So our goal here is we're going to have a voltage source here. Now I'm going to put a little squiggle there. Sometimes we still just put plus minus here. It's okay to do either. I think a lot of texts still just do the plus minus, but I'm going to do a little squiggle initially to represent that this is an AC signal. And so this is going to be some I sub m cosine omega t plus theta and current, and of course the units would be in amps or milliamps or something. And then we're going to have a circuit here. I'm going to make just a very simple circuit. R and C. And let's say we're interested in knowing what the output voltage is here. V out. Now, what we're going to be focusing on this course is, we said, AC response, or sometimes what we refer to as steady state response. Now, if we were to look at this with respect to time, there are going to be two portions of the time response. And two portions of the time response, because for instance, this capacitor isn't necessarily going to be charged up right away. And one of the portions is going to be what's referred to as the transient response. And the other one is going to be the steady state response. And the steady state response, you can think of it as after the circuit has been on for a long time. Basically, what's the response after the circuit has been on, after you've turned power on? Because let's assume here first that power is off. So if power is off, because of this resistor, this capacitor will eventually completely discharge. There won't be any voltage across that capacitor. So we know that a capacitor has to kind of charge up. So if I look at a graph here, and this isn't necessarily going to be an accurate graph of what the actual response, actually this shouldn't be IM, this should be VM. It could be current. Actually, I'll just leave it as IM. Doesn't matter that it's a current or a voltage. I'll just leave it as a current. That's fine. But if we look at the voltage there, what's going to happen here is it's going to look something like this here, in the sense that, before time, there's nothing. Because signal's not on, nothing's happening. And then it gets turned on. And so it might look something like this initially. And then it's going to even itself out. Here, let me go back here because I was trying to draw something. So it's going to kind of start off a little bit where it's like, okay, well, the circuit's turning on, kind of powering up, and then it's going to reach a spot here. So this right here is what we refer to as the steady state response. And what I mean for that is I'm going to just kind of roughly sketch this. This is still going to just go and do the same thing. It's not going to change. It's going to just look like this now for the rest of the time. And this right here is what's referred to as the transient. In essence, the power-up time. And I mean, you're all probably used to this, is that, equipment takes time to power up. And some of that's not because you have to wait for the signal to reach steady state. Some of that's just because you have to wait for something to heat up, or, like I have got an etching machine that you have to do a warm up and it spins the motor because the motor's got to heat itself up, kind of get used to spinning again, because it spins at like 90,000 RPM. So you need to kind of give it a warm up time before you actually start using it at the 90,000 RPM. And so we've got this transient and this steady state. This is what we're going to be interested in. Now, the technical way you solve these, the very technical method, is using calculus, differential equations, and some other stuff as well. But it becomes just very tedious and difficult for no purpose. What I mean by no purpose is that all we're interested in the steady state, all of those technical computations using the calculus and differential equations, all of that really is so that we can get a handle on what the transient response is. If all we're interested in is the steady state response, we don't have to do all of that. And so we're going to be using what are called phasors to analyze circuits. And this is actually going to make it complex numbers with algebra. So instead of having to do calculus and differential equations, we're going to be able to just do algebra. Yes, we're going to have to use complex numbers. That's a small price to pay, because in the previous module we've learned that complex numbers aren't that bad to deal with, especially when we have a calculator that can do the complex computations for us. All right, so let's end this video here, and in the next one we'll start talking about phasors and how we can look at what the phasor is for a voltage source or a current source, and then what the phasors are for the different circuit elements.